Think of the diffuser as the middleman between the turbo's compressor and the fiery combustion zone. Its job is super important. It takes the speedy air from the compressor and slows it down, increasing its pressure. This way, when it enters the combustion area, it's at a slower speed, perfect for keeping the flame burning strong. If it rushed in too fast, it could just put out the flame. The combustion section is like the powerhouse. It's where the magic happens. It raises the air temperature by burning the fuel mix, unlocking all that energy stored inside. Now, most of this energy is used to spin the turbine that runs the compressor, but there's some left over. That leftover energy goes on to power things like big fans, propellers, or helicopter blades in engines other than the pure turbojet. The main job of the combustion chamber is pretty crucial. Mix the fuel and air just right for a good burn. Burn that mix efficiently. Keep those scorching hot gases at a temperature that won't wreck the turbine's blades. Finally, send those hot gases over to the turbine section. The combustion section sits right in the middle, between the compressor and the turbine. They're always aligned with these parts, no matter the engine type, because they've got to keep that airflow going smoothly. All these combustion chambers have the same basic elements: a casing, an inside liner full of holes, a way to inject fuel, something to spark things up, and a system to drain off any leftover fuel after the engine's shut down. There are three main types of combustion chambers, each with its own variations. So the can-type combustion chamber is what you'll find in turboshaft engines and APUs. Each one's got an outer casing with a heat-resistant stainless steel liner inside. They're designed so you can remove the outer case when you need to replace the liner. In the older engines, each can, or chamber, had these tubes connecting them. Why? Well, when you fire up the engine, these tubes help spread the flame from one chamber to another. It's like passing the torch along till they're all burning. The tubes where the flame travels can look different from engine to engine, but they all basically do the same job. And remember those spark plugs? They're usually set in two of these chambers to get things going. One key thing with these chambers is draining any leftover fuel after shutdown. If you don't, it can cause trouble like gumming up the works or even igniting when you start up next time, pushing temperatures past safety limits. The liner's packed with holes and louvers that do some important work. They split the incoming air into two streams: primary air that mixes with fuel and burns, and secondary air that cools things down towards the back of the liner. This cooling air really drops the temperature of those hot gases from a scorching 3500 degree F to about 1500 degree F. Plus, it helps control the flame pattern to keep it from scorching the liner walls. There's always a spot for a fuel nozzle in these chambers. It sprays fuel in a fine mist, and the finer the spray, the quicker and better the burn. And there are a couple of nozzle types out there, simplex and duplex, but those get into more detail in another chapter. The igniters for these chambers work much like the ones in can-type chambers. They're typically mounted in pairs, and they've got to stick out enough to get into the combustion chamber and get things fired up. Remember those flame tubes? They link the burners together and help start the engine up, just like in the can-type chambers. They're pretty much the same, just with some differences in how they're built. The can annular combustion chamber, you won't spot that in modern engines these days. It's got this forward face with 6 openings in each chamber, and these match up perfectly with the 6 fuel nozzles. They're a dual orifice type, needing a flow divider which helps in pressurizing the fuel. Around each nozzle there are these cool pre-swirl vanes. They do a neat trick, swirling the fuel spray, which makes the fuel break down better and burn more efficiently. Those swirl vanes are pretty important because they make the flame do 2 things: burn fast and not shoot off too quickly in a straight line. That kind of turbulence at the start of the burn is actually what you want. It's like making sure everything's mixed up really well, because just relying on the air and fuel to mix on their own takes too long. These chambers need to have those drain valves set in a couple of lower spots. That's for clearing out any leftover fuel after the engine's been shut down, ensuring it won't cause issues during the next start. The way air flows through these can annular chambers? Pretty much the same as in other burners. There's this special setup that twists the airflow and gets it all turbulent, which helps with the combustion process. In figure, you can actually see how the air flows. There are different types like combustion air, metal cooling air, and gas cooling air, all going in different directions. Now, the basic parts of these annular combustion chambers are just like the ones in the can type. You've got a housing and a liner, but here the liner's this circular shroud that wraps all around the turbine shaft housing. They make these chambers with heat-resistant materials, sometimes adding thermal barriers like ceramic coatings. And if you check out figure, you'll see how they've set up louvers and holes to make sure the flame doesn't mess with the sides of the combustion chamber. Turbine section. The turbine's this powerhouse that takes the energy from the exhaust gases and makes it into mechanical power to run stuff like the compressor and other engine gear. You know, it's a bit like a recycling deal. It snags about 60 to 70% of the pressure energy from those gases and puts it to work. Now, how much it grabs depends on what it's spinning, like the size of the compressor or how many accessories it's dealing with. This whole turbine business happens after the combustion chamber. It's kind of like the combustion chamber's neighbor sitting right behind it. So this turbine setup, it's got a couple of key parts: the turbine inlet guide vanes and the turbine disc. Think of those vanes as sort of a nozzle diaphragm or guide that comes right after the combustion chamber and just before the turbine wheel. And here's the tricky part: they've got to handle the hottest temperatures in the engine, so they need to be carefully looked after. Once the combustion chamber's jazzed up the airflow with heat energy and sent it over to these vanes, it's the vanes' turn to get things prepped for the turbine rotor. Those stationary vanes are shaped and angled in a way that turns some of that heat and pressure into serious speed. They basically turn some of that pressure energy into speed energy, and that's what drives the turbine blades, making the whole setup tick. Now, there are a few types of turbine blades: impulse, reaction, and a mix of both, called reaction impulse. The impulse one's sometimes called a bucket because when the air hits the center of the blade, it changes direction, making the whole rotor and disc spin. These nozzle guide vanes can even be adjusted during an engine overhaul to make the airflow smack into those blades in a more efficient way. Reaction turbine blades work by using the airstream's aerodynamics to spin the disc. They're designed to get the most power efficiently from the turbine engine. Now, the reaction impulse turbine blade is like the best of both worlds. At the root of the blade, it's more bucket-shaped like the impulse one, and as it goes toward the outer end, it's more like the airfoil-shaped reaction blade. But wait, there's more to these turbine inlet nozzles than just being a guide. They've got another job: to redirect those gases at just the right angle for the turbine wheel to spin in the right direction. It's like aiming a basketball into the hoop. It's got to go in the right way. These nozzles are a bit of a construction marvel. They've got an inner shroud, an outer shroud, and these vanes that are wedged in between. The number and size of these vanes change depending on the engine type and size. And hey, check out figure. It shows the different ways these vanes can be put together, either loose or welded. Now, these vanes need to handle temperature changes without warping or getting all bent out of shape. One way to handle this is by setting up these vanes in slots in the shrouds, giving them a little wiggle room for expansion. Then there are support rings around these shrouds to add strength and keep the vanes in place when the shrouds are moved. Another trick is welding or riveting the vanes into the shrouds. But to handle the expansion caused by heat, they chop up either the inner or outer shroud into sections. These cuts allow for just enough room for expansion without stressing out the vanes. Smart engineering, huh? Check out figure for a closer look. The turbine section's got this dynamic duo, a shaft and a wheel shown in figure. The wheel is like a high-tech fan with blades stuck to a spinning disc. When the hot gases rush out of the turbine inlet nozzles and hit these blades, they give the wheel a serious spin. But all this spinning creates a lot of force and heat, so keeping things at safe temperatures and speeds is crucial. Now, this disc, that's what the wheel is before the blades get attached. It's the backbone for those blades. Once the blades are on, voila, you've got yourself a turbine wheel. This disc's got to handle a lot, dealing with high temps from the gases and absorbing heat from the blades. And you know what? It's the rim of the disc that gets really toasty, way hotter than its inner parts. That creates a mix of stresses, both from rotation and temperature. To ease this, cooling air is often directed onto the disc's face. There's a neat trick with these discs. Little grooves or notches are carved out to match the blade roots. These notches let the blades attach to the disc and give the disc room to expand when it's heated up. When the engine's running, the disc expands and the clearance between the blade root and the notch gets snugger, holding the blades firmly in place. Have a look at figure. It shows how the turbine blade gets secured with this fir tree design and lock tab method. The turbine shaft is the muscle here, made of tough alloy steel, see figure. It's got to handle the heavy torque thrown at it. Now, connecting this shaft to the turbine disc can be done in a couple of ways. Sometimes they weld the shaft onto the disc, or they bolt it on using a hub on the shaft that fits snugly on a machined surface of the disc. Bolting is the more popular option. It's more common in these setups. The turbine shaft's also got to team up with the compressor rotor. Usually, there's a special spline cut at the front end of the shaft. This spline hooks up with a coupling gadget between the compressor and turbine shafts. Sometimes, if there's no coupling, the splined end of the turbine shaft fits into a groove in the compressor rotor hub. These setups differ based on the type of engine. Centrifugal compressor engines usually go with the splined coupling, while axial compressor engines can use either method. When it comes to attaching turbine blades, they've got a method that's pretty slick. They use this fir tree design. It's a secure way to keep those blades in place. Blade retention in turbines is no simple feat. It's done using various techniques like peening, welding, lock tabs, or riveting. Check out figure. It shows a turbine wheel held together using rivets to keep the blades in place. Now, one trick for keeping blades snug is peening, kind of like crafting a tiny notch in the edge of the blade fir tree root before it's installed. Then, when the blade's in the disc, the metal flows into that notch, securing things in place. Another method is building the blade's root to include its own locking mechanism. Picture a stop on one end and a bent tang on the other. That tang locks the blade into the disc, keeping it firmly in position. Those turbine blades? Well, they can either be forged or cast. Most are precision cast and then polished to get that perfect shape. They often craft these turbine blades as a single crystal, giving them better strength and handling high temperatures like a champ. And hey, they add heat barrier coatings and cooling systems to keep these blades and nozzles cool. Check out figure. It displays a turbine blade with air holes for cooling. You know, turbines usually have these open blades on the outside, but there's another style. Shrouded turbines. These blades sort of band together around the wheel's edge, improving efficiency, reducing vibrations, and allowing for lighter weight, although they do need more blades and have limits on speed. Now, sometimes one turbine wheel just isn't enough to handle all that power from the exhaust gases, so they add more stages. Each stage has got fixed vanes or nozzles and rotating blades. In certain turboprop engines, they've even used up to 5 turbine stages. And guess what? Each wheel's got its own nozzle up front. Engines that need to handle heavy loads might require multiple turbines or compressors. See, when you've got more than one turbine wheel, you're often dealing with serious rotational forces. This can also mean multiple compressor rotors to balance the power. In some setups, it's just one turbine rotor doing all the work, driving everything in the engine. Look at figure for a peek at this single-stage rotor turbine. Simple, light, and compact, perfect for certain engines like the basic pure turbojet. Now, for the big players, check out figure. That's a multi-stage turbine. Engines like turbofans often have 2 spools, each with its own set of turbine stages. One spool's for low pressure, like the fan, and the other's for high pressure, the high-pressure compressor. Look at figure for an illustration of this setup. Last but not least, the turbine casing. It's the home for the turbine wheel and nozzle vanes. This casing offers support to the turbine's stator bits and bolts right onto the combustion chamber housing and the exhaust cone assembly. Take a peek at figure 172 to see what it looks like. Exhaust section. So the back end of a gas turbine engine, right after the turbine, has this section called the exhaust part. It's got a bunch of parts working together, all with their own jobs, but the main goal is the same. They've got to guide the super hot gases backward without making them all turbulent and make sure they shoot out at a really high speed. Each part does its own thing to control how the gases flow. This exhaust section sits right behind the turbine and finishes up when those gases zoom out of the back as fast exhaust. This section is made up of a few things. There's the exhaust cone, sometimes a tailpipe, and the exhaust nozzle. The exhaust cone is pretty crucial. It gathers up all those hot gases coming out of the turbine and sort of smooths them out into a solid flow. It slows the gas down a bit and cranks up the pressure a bit. This happens because the space between the outer duct and the inner cone gets wider towards the back. The whole setup for the exhaust cone includes an outer duct and inner cone, about 3 or 4 struts or fins, and some tie rods to help hold everything together. This outer duct is often made of stainless steel and hooks up to the back of the turbine case. It's responsible for catching those exhaust gases and sending them straight to the exhaust nozzle. The duct's got special features built in, like spots to attach temperature sensors called thermocouples and holes for those tie rods I mentioned earlier. Sometimes, instead of those tie rods, the inner cone is only supported by those hollow struts. They're welded onto the duct's inside and the inner cone itself. And those struts? They're not just for holding things up. They also play a role in making sure those swirling gases leaving the turbine don't go all wonky at a 45-degree angle. So you've got this inner cone right in the middle, sitting close against the back of the turbine wheel. It's there to make sure things don't get too crazy as the gases leave the turbine. This cone gets some help from those radial struts, which help hold it in place. Sometimes there's a tiny hole at the tip of the cone. That hole does a pretty cool thing. It lets some cooler air come in from the back of the cone, where the gases are kind of high pressure. This air then heads inside the cone, cooling down the turbine wheel's face. Since the turbine wheel is spinning, there's not much air pressure there, so this airflow is pretty much guaranteed. The cooled gases go back to the main flow path by sliding through the space between the turbine disc and that inner cone. The exhaust cone assembly is basically the end part of the engine. The last part is the exhaust nozzle, which is considered more of an airframe component. Now let's talk about the tailpipe. It's often made a bit flexible. Some of them even have this bellows setup that lets them move around during installation, maintenance, and when they expand with heat. That flexibility helps prevent stress or bending that might normally happen. Heat coming from the exhaust cone and tailpipe could mess with the airframe parts around them, so there's insulation in place. Two common ways to protect the fuselage structure are insulation blankets and shrouds. Those blankets, shown in figures, have layers of aluminum foil separated by fiberglass. They do a great job of not just shielding the fuselage, but also reducing heat loss from the exhaust, which actually helps the engine work better. Then there are these exhaust nozzles, two kinds actually. The converging design is for slower gas speeds, while the converging-diverging one is for supersonic speeds. They're both super important. The fixed-area nozzle is simpler, no moving parts, but the size of its opening is crucial for the engine's performance. Too big and thrust is wasted. Too small and the engine might choke or stall. The variable area nozzle is used when there's an afterburner in play. It opens up more when that's activated and shrinks down when it's off.